Thank you. I'd like to acknowledge my co-authors. This is a result of, this is actually abstracting data from a number of field studies that have been done for other purposes. Why look at acetonitrile? Well, biomass burning is a major driver of climate change. It has a role in climate variability, and so therefore, because acetonitrile is recognised as an ideal tracer of biomass burning plumes, it seemed interesting to take the question one step further. Well, what happens in the remote atmosphere away from biomass burning to acetonitrile? Just to quickly run through the sources of acetonitrile. Biomass burning definitely is a major source, and as time goes on we get to understand that source better. We get to understand that smouldering burning has greatly enhanced acetonitrile emissions compared with flame burning. But we also get to recognise that there's a lot more biomass burning in the world than what we initially thought many years ago. Such things as garbage burning and biofuels burning need to be included in the global estimates. But as it turns out, all the other sources that we've looked at, loss from synthetic production, from vegetation, production in the atmosphere by methyl isothiocyanate, actually fertilizers to give acetonitrile, but all of these are essentially negligible sources compared with biomass burning. So this is where I'm showing the results of studies which, as I say, have all been done for other reasons. 3 studies in Western Australia, about 150 kilometres south of Perth, on the escarpment there in rural landscapes. Several campaigns at Cape Grim, a baseline station which essentially sees the Southern Ocean. Studies in Sydney, rural Sydney and Wollongong, where one can in fact at a coastal site see the marine air coming in, so you get a mixture there of urban, rural and marine air, and you can sort that out. And a ship cruise, that was the SOAP expedition or campaign off the Chatham Rise, a couple of 100 kilometres east of New Zealand. It's all in one latitude band, but in fact it gives us a lot of data, about 580 days of data, which compares with, in the Southern Hemisphere prior to this, there were 36 days of acetonitrile measurements, so a 15-fold increase. We now can put some good numbers on the Southern Hemisphere. Oops. And this is what we get. Here, most of that data is all compressed into this. So this is more than 500 days of data over 8 field campaigns. And what it essentially shows you is that in the mid-latitudes of the Southern Hemisphere, the concentrations are statistically significantly lower than what you get in the Northern Hemisphere tropics, temperate latitudes, or polar latitudes. The whole global distribution is consistent with the knowledge that we have of biomass burning emissions primarily in the Northern Hemisphere tropics. So now I'll show you a little bit. In the free troposphere, we have only one measurement in the Southern Hemisphere compared with the Northern Hemisphere. Now, I should clarify where these Northern Hemisphere measurements come from. I went through, or my colleague Wayne Kirsten did this part of it, we went through slightly less than 100 papers which had studies in the Northern Hemisphere. They are primarily to do with biomass burning. But in them, in 55 of them, there were measurements provided which were away from the plume. So that's where these points come from. In many cases, they're only 1 or 2 days data, but that's what's available. What you see here again, this is the results of these 500 days measurements, significantly lower. This is the continental boundary layer. And this is the marine boundary layer in the southern hemisphere. And you see very clearly how it differs from the marine boundary layer in the northern hemisphere. Well, to ask how we can get more understanding out of this, this allows us to constrain, and I used a very simple global box model with 2 hemispheres and boundary layers and an interactive ocean. And one can fit the model. It has a prescribed chemistry in it. It's fixed chemistry. And I fitted it to this, optimized the fit to this data. And this is what you find, is that you have a very minor removal from gas phase OH, as people have known. There was the opportunity of exchange in both directions over the land surface, but in fact the solution was for a significant loss at the land surface and a loss over the oceans, which is slightly less than, but comparable with that found by Singh over the North Pacific in 2003 from aircraft measurements, giving a total loss which in fact matches the emissions that were prescribed in the model. This is what the model tells us a little bit, that most of the acetonitrile would be in the ocean surface layer with only a small amount in the troposphere and some in fresh water. And what we can recognise by the behaviour of the Henry's law constant, which is strongly dependent on temperature, is that as water moves backwards and forwards latitude-wise, it would lead to release of acetonitrile to the atmosphere and ocean uptake. The model results suggest that the lifetime of acetonitrile over land, in the troposphere is about 80 days, but in the ocean about 11 years. And that's the reason for that long reservoir. Coming to the next, I ran the model over the last decade, or last 2 decades, particularly looking at the Indonesian fires, which were the major source of peat burning over the last 2 decades. Now, there in the red is the continental boundary layer. Remember, that's averaged over the whole of the hemisphere. And this is the amount in the northern hemisphere ocean. These are northern hemisphere results, and that's in the marine boundary layer in the northern hemisphere. The interesting feature is that while in an equilibrium situation, the concentrations go up and down each year, there is a residual carryover from the amount of the Indonesian fires over the subsequent few years. And this is because the ocean is working as a buffer reservoir. Well, the question is this a reality? Well, here are the results from the same period of time taken from those atmospheric observations. They're all the observations we have in the northern hemisphere in the 1990s and 1980s. We have none, unfortunately, at the time of the fires, but in the years following the fires, we had quite significant number of measurements, decreasing slowly over a period of years. Now, the only way you can explain that decrease is by the action of a second reservoir, a buffer reservoir, i.e. the oceans. So I think this is fairly conclusive proof of the role of the oceans in the atmospheric cycle of acetonitrile. So with that, my conclusions, we've now got sufficient information to make a new assessment of the global cycle of acetonitrile. I think the first assessment of it was made by Guy Brasioro more than 30 years ago, but we have more information since then. That we have to recognise the role of the ocean in the acetonitrile global cycle, and I think importantly, as we develop, and we're currently reaching the stage where we can have long-term measurements of acetonitrile in the atmosphere, these long-term measurements will effectively provide a record of the biomass burning that's occurring globally. So it's a new useful tracer for globally for biomass burning. And finally, the other obvious consequence is that we can't deal with the atmospheric cycles of polar VOCs without including a dynamic ocean layer. That's an essential requirement. Thank you very much.
Thank you, Ian. We have time for a couple of questions.
Hello, Ian. Thanks. Nice talk. I just wondered, is the lifetime in the ocean the same everywhere, and do we understand what's driving that?
Look, that's a consequence of the model, and the model, to achieve the solution, one had to prescribe it the same everywhere. There are three mechanisms for removal of acetonitrile in the ocean. One is it could be the removal, it could be the actual loss of surface layer water to deep water, but that would take about 30 years, so it's not that. It could be removal by OH, but in fact if you do the OH calculations it turns out to be a trivial amount. Four mechanisms actually. It could be removal by microbial grazing, and if you look at microbes, they're very efficient. You know, acetonitrile is another source of food for them, and so I would place that very highly. There's a possible basic hydrolysis of acetonitrile, but unfortunately it's hard to dig out. People say that it's very slow, but it's hard to find the original kinetic data for that. Yeah.
Great. Hanwa, you have a question?
Yes, Ian, very nice talk. Just a question, is this oceanic removal biological in nature? And an ancillary question is, you think almost exactly the same thing is happening with HCN?
Sorry, I couldn't hear the second part of that.
Is exactly the same thing happening with HCN, which is also an identical kind of a tracer for biomass burning?
Okay. Look, I haven't. On the first one, I think with regard to the ocean source, the biological is the most logical source. And look, one of the sources of information about biological consumption of acetonitrile is that it is used in industries, and there are studies about what happens when it passes into soils and things like that, and microbial consumption sufficient. HCN is a very similar molecule, and it's produced by biomass burning, and it has some of the same properties in the atmosphere, but I haven't extended this study to cover HCN, so I can't give you an answer to the second question. Thanks.
All right. Thank you.